Welcome to the Insightful Professor. In today's presentation, we continue our examination of variables and assignments, or expressions and assignments. We're going to go a little bit deeper into this topic. First, we review what we discussed in the earlier video, the basic assignment statement. Remember that this provides a way to take a value and place it into the memory location associated with the variable. What we do is we put the name of the identifier, follow that with the equal sign, which is our assignment operator, and then an expression. The expression could identify another variable whose value will be copied into this variable's memory location. It could identify a constant value, or literal. It could identify a more complex expression. We provide a couple of examples here. Here we're taking a literal or constant value of 100 and assigning it to number of items. In the third example, we're taking a complex expression, evaluating that expression. The result of the evaluation then gets placed in the memory location associated with total weight. And again, for more detail on that, review the previous video. Well, let's talk about a couple of the options here. Let's talk about the literals, or the constants. A literal is the source code representation of some fixed value. The point is that the value is identified directly within a statement. It's not the name of a variable or some identifier that refers to a memory location, but it actually introduces the value itself right within the statement. There are different types of literals depending upon the data type that you're using in your expression. So each type that we have, each of the 8 primitive types, allows for some kind of a constant value to be injected directly within a statement. So let's talk for a moment about integer literals. Here we're saying you can express the actual value, or the literal, or the constant, using decimal, hexadecimal, or binary. Decimal, as you're probably well aware, is base 10. Hexadecimal is base 16, and binary is base 2. Here we look at the value 26 in decimal. Then we show that same value, but expressed using hexadecimal. So it's a hexadecimal 1A. The interesting thing that we point out here is that the X, which indicates hexadecimal, could be uppercase or lowercase. It's case insensitive. Then the A, which is a hexadecimal digit. Remember, hexadecimal has 16 digits, 0 through 9, and then A, B, C, D, E, F. If we're using A through F, that could be inserted here in the literal as lowercase or uppercase, also case insensitive. The third value here is a binary representation of the decimal 26. So we have a B indicating binary, and once again this could be uppercase or lowercase, case insensitive. And then we have the string of 1s and 0s corresponding to the binary digits in this particular binary number. We also can have a floating point literal. And here we're showing that we can have a floating point literal that could be float or double, and the F to indicate float or the D to indicate double. Those are also case insensitive. Uppercase, lowercase works fine for the F or the D. And again, those represent single precision and double precision values. So what we're showing here would be 18 with a decimal point, indicating that this is not an integer. Technically, this is a floating point. And likewise, 1.8 E1 using a scientific notation. And also we note that the E, which represents the exponent or the scientific notation, could be presented using uppercase or lowercase. Again, a lot of flexibility here. When we're dealing with character data types, we can use char, and we can introduce a literal, which uses single quotation marks or apostrophes. So here's the character A in uppercase, the character for 9. This is not a numeric value, this is the character representation of the digit 9. and then the pound sign or any other special character. Again, these are enclosed within what programmers tend to call single quotes or apostrophes. In addition, we could have a string literal. Remember, string is not a primitive data type, but actually it's a built-in type or pre-declared class, so that when we use string, we're actually creating a string object. That string object could be an identifier that we create, and then we assign a variable to the memory location to which it makes a reference, or it could be a literal. And when we have a string literal, we enclose this within what programmers call double quotes, the true quotation mark. So this is actually a string literal, and we distinguish that by allowing multiple characters to be contained between the double quote or quotation marks. Rather than inject the literal value, it's very common to create a variable that has a value which we'll treat as constant and make it such that that variable can never be changed. It can be assigned a value one time when it's declared, when it's initialized, but can never be assigned a value again. This type of an identifier is referred to as a named constant. This is very convenient and often is the correct way to deal with using constants within a program. Say, for example, we have something representing a tax rate, and we're going to use that in computation in several places in the program. If we use a numeric literal and inject it within the statement, what happens if the tax rate changes and we need to modify the program? We would have to find every occurrence of that literal value, which represents or means the actual tax rate, and then change it. But there could be other instances of that value within the program that mean something different than that tax rate. So if we did a global change, we could be inadvertently changing something that we don't wish to change. But by having a named identifier or a named constant, we associate this name with a particular value, use the name wherever we wish to use that value as a constant, and then should we need to modify the program and change the value, we change it in exactly one location where that named constant is declared. And then we're not going to inadvertently change something that we didn't want to change. So how do we achieve this idea of creating a variable with a value, but the value can never be changed after the declaration? Good question. Well, the way we do it is by using the keyword final. So we would say, here's the data type, such as int, here's the identifier, and then here is the value. Again, this will be assigned, but this will be the final or the last assignment that we ever do to this variable, and we denote that by using the final keyword. This is what makes the identifier a constant. We can refer to max throughout the program to be able to look at the value, but we can never do another assignment. The compiler will prevent us from being able to do that. So this is the first and only, it's the final assignment, hence the final keyword. This makes it a named constant. Now, to have this stand out in code, remember we talked about naming conventions or naming standards. For a regular variable, we would start with a lowercase letter. Well, here we have all of the characters in uppercase, and this is a standard convention that most programmers have adopted to indicate that this is a named constant identifier. If we see this being used in some kind of an assignment statement, we'll see that, oh, this value is declared as a constant elsewhere in the program. This is not a variable, but it's actually a constant identifier. And a couple more examples are shown here. Let's get on to the operators and expression. Java allows us to use variables, constants, and arithmetic operators. And the arithmetic operators are plus for addition, minus for subtraction, asterisk for multiplication, slash for division, and then the percent sign for an integer division where we're looking to achieve or produce a remainder. So examples of how this would be used, these are said to be infix operators because we have the two things that we're operating on, and in between the two operands, we place the operator. These are binary. They take two operands, and again, they are infix in that we put them in between the two things that we're operating on. So some quick examples are shown here. Now, what's pretty neat, but sometimes confusing, is that we can kind of condense some of our assignment statements using a kind of shorthand notation. Java is not the only language that supports this, so it's something that if you've seen other languages, such as C or C++, then you may very well be familiar with this. So this idea would be we can take our arithmetic operations, and what we can do is, instead of saying variable or identifier, and then operator, and then another variable identifier or expression, the idea of the infix format, what we're able to do is we can take the operator and use it together with the assignment operator. So we can take the numeric operator and the assignment operator and combine them. So this is sometimes called a combined operator. Not a surprising revelation there, right? So what we have is we could say something like total weight plus equal unit weight. This would be the same as saying total weight plus unit weight is assigned to total weight. So these two guys here are equivalent. They're just alternative ways of expressing the notion. So you might say, well, it's a little confusing. I'll just go with this long way of saying it. Well, the problem with that is a lot of programmers tend to like this shorthand or abbreviated syntax. So even if you choose not to use it in writing your own code, you have to at least be able to understand it to read someone else's code. So it's well worth spending a couple of moments to get comfortable with the idea that these two assignment statements are equivalent to one another. So what we're doing is putting the result into total weight. So we're saying add to total weight whatever's in unit weight. This does the same thing. It says add to total weight whatever's in unit weight and put the result into total weight. That's the combination of the two operators. And again, all of these arithmetic operators will work: add, subtract, multiply, divide, and then the remainder operator as well. In addition, there are some other kind of bitwise operators that work in this same way. They can be combined with the assignment operator. Here's a quick overview of those 5 numeric operators that we identified with a few examples. So I'll let you take a closer look at this and just make sure you're comfortable with it. Feel free to pause the video and spend a little bit more time on that. Assignment compatibility is another important concept. What happens is when we declare a variable, we declare it as being of a certain data type. Java will not only allocate a certain amount of memory based upon what that data type is, but it will also restrict operations as to what the values are that can be stored there. For example, if I say int, it allows for a 32-bit or 32-digit binary integer to be stored. It will not allow me to put a floating point there because the storage has been defined such that it can only store the binary integer. So the data type not only determines the amount of storage, but it also determines what are valid values. So in this case, with var1 having been declared as an integer, this assignment statement causes a problem. 3.14 is not an integer, it's a double. An attempt to do this would result in the compiler bringing to our attention the fact that something is wrong, that there's an error. This is referred to as a type mismatch, or sometimes incompatible types. The idea is that you cannot put a floating point value into an integer storage. So certain assignments are acceptable, but this is not one of them. So what happens is we can see what's acceptable by looking down here. I can put a byte, which is a very small integer, into a short, which is integer storage for a slightly larger integer. And I can put a short into an integer. Those are all fine. In fact, I can put any of those into a long because these are all integer storage, but they're of different sizes. So notice I've indicated with kind of an arrow the direction of permissible assignment. I cannot put a short into a byte because what happens is I've got a big thing and I'm trying to put it into a small space. That's not going to work. So I can go only in one direction here with the assignments. Notice any of the integers could be assigned to a floating point, be it float or double, single precision or double precision. So the direction of assignment is important to become familiar with. One other thing that is worth taking a look at here is very often we talk about things like numbers that really are characters. For example, if we talk about a part number, we have part number 27, for example. 27 is technically not a number with which we would do arithmetic, but it's some kind of an identifier. So in that case, the 27 would be put within quotation marks, indicating it's a string, it's a character. So that's what we see here. If we assume that message has been declared as a string, then message can only receive or be assigned a string value. Quote 123 is a string literal. This assignment is correct. It's legal. But 123 is an integer literal, and we cannot put that into a string variable or the storage for a string that value. So keep in mind, there's a little confusion that sometimes occurs here. The system is not automatically going to convert the data from one type to another for you. We'll look at how this can be done in a later video when we talk about what's called type casting. Here, this would be something done explicitly. We tell the system to do this conversion. But when it comes to automatic conversion, there are not many times that it's going to work the way you would want it to. In fact, it may not work at all. Therefore, you want to keep this in mind, that this would not be legal. Putting something of one data type, assigning it to storage that's designed to hold something of another data type. Now we come to operator precedence. This is something that's important when we're working with complex arithmetic expressions that have a mix of operators. If everything is addition or everything is subtraction, it's pretty straightforward. But if we have mixed operators that have different precedence, remember things like multiplication and division would be evaluated before addition and subtraction would be evaluated. So what happens if we have a complex expression that has a mix of these different operations? The concept of operator precedence comes into play. This indicates when a particular operator would be evaluated relative to another operator. So we have higher and lower operator precedence. When you're dealing with mixed operator expressions, Java will kind of insert parentheses. That'll make it a little easier for us to understand. It doesn't actually do this, but we can think of it being done to see how the operators are going to be applied. Let's consider a simple case of equal precedence. We have base plus rate plus hours. So it doesn't matter really how we evaluate this when we're doing addition. So what happens is Java can be thought of as interpreting this by saying, well, let's take these first two things, group them together, do the addition, then we'll add the next thing. So it kind of implicitly is inserting parentheses. What happens when we have different precedence? This is where it gets interesting. So we have base plus rate times hours. It doesn't simply go left to right and say, let's add base and rate and then multiply by hours. That would be incorrect, because remember, the arithmetic operators say that the multiplication should be evaluated before we evaluate the addition. So this is how Java would handle it. It interprets it as saying, let's take these two things that are being multiplied and do the multiplication first. Then we'll go back and do the addition. And hopefully you're comfortable with parenthesized expressions of this sort. Okay, we write it one way and Java interprets it in a certain way, as shown in these two examples. And hopefully that makes it fairly clear to you. So next we talk about one more little example where we have parentheses being used within an expression. So that is, we kind of have nested parentheses. Here we're showing 4 multiplied by 5, and we're forcing that to be done by putting that operation and its operands within parentheses. Then we have 5 minus 2. Then we're dividing one by the other, so we have parentheses to say let's do that before we finally do the subtraction. So we're controlling the order in which things are evaluated. So when we're doing this, we say if 2 sets of parentheses are at the same level, they're going to be processed left to right. And that's what we're seeing here. These 2 are effectively at the same level, so we do the multiplication first because this set of parentheses and its enclosed operand and operators appear to the left of the 5 minus 2. We then evaluate that, and then we can do the division that appears here, and finally the subtraction, which occurs outside. Think about this one for a moment. It's kind of interesting. 4 times 5 will give us 20. 5 minus 2 is 3. 20 minus 3, what's the result? Well, you can see over here that we're showing the overall result as an integer. Therefore, the assumption in this particular example is all of this is integer, okay? Remember, 4 is an integer literal. 5 is an integer literal. This is not 4.0 or 5.0, which would make these doubles. These are all integers. So we have the 20, and we divide that by 5 minus 2, which is the 3. 20 minus 3, what is that going to be? It's not going to be 6 point something because these are integers. It's going to be 6. So this expression here will yield a 6. 6 then minus the 25 is what gives us the negative 19. So bear in mind that these are all integers. Hence, this division is interpreted as an integer division. There's no decimal result. Okay, that's a little tricky, but you want to pay close attention to such things as you're looking at arithmetic expressions and operations. And that brings us to the end of the presentation. Hopefully you found the information useful and informative. If you'd like to offer any comments, do so by putting those in the comments section below. And once again, thanks for watching.